Hi everyone. So this is a summary lecture on first order logic. We have already seen the propositional logic. In this propositional logic, what happens? Every variable, what is the domain of every variable in the propositional logic? So if you see in this propositional logic, every variable, the domain of every variable is basically true, false. In this, every variable is a propositional variable. Every variable that is a Boolean variable, or I can say that is a propositional variable, and the domain for every variable for this propositional variable, what is the domain? The domain is basically true, false. So this is the domain. Either the value can be taken is true, or the value it can take is false. So remember, in this propositional logic, every variable, whatever variable you take, for example, if you take variable a, then that variable a comma b, whatever, so the domain of these variables is basically true, false. These variables can be either true or they can be false. So these variables, they can take value from this domain. So this is the domain, or you can say universe. From this domain they can take the value. This a can be true, this a can be false, but one of them, of course. So because this is a set, this domain is basically set of values. What is this? This is a set of values. So this variable a, it can take one of these value. This variable b, it can take one of these value. This is the domain in propositional logic for every variable. So you can see this. So true, false, these are the two values these variables can take. These are the propositional variable. Now for example, if you assign this p true and this r true, if you assign this q false and s false, then what will be the truth value of this expression? Can anyone tell me? For this expression, what will be the truth value? What is going to be the truth value for this expression? If you take p true, r true, q false, r false, if you take this, then what will be the truth value of this expression? So you can easily see, first of all, more priority, you can see precedence of this conjunction, it is more than the precedence of this implication. So first you will do this p and q. This p and q, this will be false, correct? This p and q, this is going to be false. False implies anything. False implies anything. False implies anything that is true. So you can see the truth value will be basically true. So this expression will be true. Very simple. Similarly, you can do this like what I can do. This is a propositional variable. This is propositional variable. So the domain of these variables is true, false. You can assign them true or you can assign them false. This is the domain for propositional variables. Now, if I do this assignment that p is false, s, r, q, these are true, then what is going to be the truth value of this expression? For this expression, what is going to be the truth value? What will be the truth value for this expression? So again, you can see that p and q, again this will be false. Again, this is going to be false. And false implies anything. False implies anything. False implies anything that is true. So for false implies anything, remember, false implies anything that is true. So you can see this expression will evaluate to true in this case also. So the point is very simple, that in the propositional logic, every variable has only this domain. Every variable can take value from this set. Either a variable can be true or it can be false. This is what happens in a propositional logic. In this propositional logic, this happens. Now, in first order logic, what happens? In the first order logics, in this first order logic, variable, it can refer to any domain. So remember, the variable, each variable can have its own domain, and that domain can be anything. For example, what can happen, that let's assume these are in the first order logic, you can have different variables like x, y, z, these different variables you can have. And what can happen, for example, maybe the domain of this variable, is set of natural number, domain of this variable is set of integers, domain of this variable is, let's assume, true, false, domain of this variable, let's assume, domain of this variable is, for example, let's assume 2, minus 3. So like this. So in the first order logic, every variable can have a domain. Every variable can have a domain, and remember, different variable can have different domain. Different variables, they can have different domains. Okay. So this is the idea about first order logic. Now, so this is what happens in the first order logic, that every variable, whatever variable you take, each variable, it refers to a domain. It refers to a set from which it can take values, and that is called domain of that variable. And remember, different variables can have different domain. Like these are the different variables, they are having different domains. So what is a domain in first order logic? This is the set of values. This is the set of values. This is the set of values a variable can take. Okay, set of values a variable can take. So remember, very simple point I want to tell you, that this m, this has this domain, this is the domain, so this m refers to this domain. Okay, so this domain, then remember this m cannot take value 1, this m cannot take value 4. Okay, this m cannot take value true, because this true is not in the domain of m. In the domain of m we don't have true, in domain of m we don't have 4. So this m, either this can take value 2 or this can take value 3. Similarly, this x, it can take any natural number, x cannot be negative. Similarly, y can be any integer, y cannot be 0.3. Okay, so like that. Similarly, z can be true or false, z cannot be 2, z cannot be 1. Okay, so like that. So this is what happens in the first order logic. So this concept of domain we have seen, this is the first concept. Remember, this is your first concept of first order logic, that every variable in the first order logic has a domain, and domain is set of values a variable can take. And remember, a variable can only take values from its domain. A variable cannot take any value outside of its domain. Every variable, this variable x, it can take values from its domain only, it cannot take any value outside of its domain. So this concept of domain we have seen. Now the next concept is predicate. What is this concept of predicate? This is another simple concept. Predicate is a statement. So you can read this definition. Predicate is a sentence. Basically, I can say predicate is a sentence. Predicate is a sentence involving variables. It will involve variables where each variable has a domain. Each variable can take any value from its domain. So every variable has its domain. Remember, different variable, they can have different domain. So different variables may have different domain. So what I'm saying, that predicate is a sentence involving variable such that every variable can take value from its domain. Every variable has a domain, and this is important. When we replace all the variables with a specific value from their domain, from their own domain, then we get a proposition. This is the definition of predicate. What is a predicate? Let's understand this predicate with one example. Consider this predicate: x is greater than 4. Let me assume that domain of x I am giving you, that is set of, let me assume the domain of x is a set of positive integers. Okay, let's assume this is the set of positive integers. Now you can see that this statement involves variable. You can clearly see this is a variable. Okay, so this is a sentence which has variable. Let me call it p of x. I am calling it p of x because there is this variable x, so that is the reason I am calling it p of x. Now you can see, if I replace this x with a specific value from its domain, this domain of x is positive integers. So if I replace this x with a specific value from the domain, like if I do this, then it will become a proposition. Now you can notice, now this is a proposition because now this is true or false. So now this has become proposition, and you can clearly see that the truth value of this is true. Similarly, you can notice, if I replace this x with the 2, because 2 belongs to the domain. The domain of x contains 2. The domain of x is positive integers, so it contains 2. Now if I replace this x with 2, then I will get 2 greater than 4. Now this is also proposition because either this is true or this is false. You can clearly see that this p2 is basically false. Okay, this is basically false. So this is the idea of predicate. What is a predicate? Very simple concept. Predicate is a sentence involving variables. There is a variable. Every variable has a domain from which it can take value. This variable x has the domain positive integers. So this variable x can take any value from this set of positive integers. Now you can see in this predicate, if you replace this variable by a specific value from the domain, then it will become a proposition. So this predicate becomes a proposition if you replace every variable by some value. Like consider this example. This is the example. You can notice px is x square is greater than x. Now this is your px. What is px? So in this px, this is the px. Px is saying that x square is greater than x. Now what this statement is saying? Now what is this? So if I replace this x with 1, then what will be the truth value? This will become a proposition. At this point of time, this is not a proposition. Why this is not a proposition? Because it contains variables. So you can clearly see this is not a proposition because this contains variables. So you cannot say it is true or false. This is not a true or this is not false. Okay. Statements which involve variable, these statements are not propositions. So you can clearly see this is not a proposition because we need to know the value of x to decide whether it is true or false. We need this value of x. Now if I replace this x with 1, then what I will get? Now I will get a proposition. Now this is a proposition. So please understand that in any predicate, if you replace all the variables, you will get a proposition. Okay. In any predicate, in any whatever predicate you take, in any predicate, once you replace all the variables by specific values, like this x I am replacing with 1, now it will become a proposition. Clearly this is false, so I can say that this p1 is false. What I can say? I can say this p1, this is basically false. Now similarly, if I replace this x with 3, then what it will become? It will become 3 square greater than 3. It will become a proposition. Again this is a proposition. So again, and this is a true. So I can say that this P3, this is true. Okay, this P3, this is true. So very simple. This is the concept of predicate. So what is a predicate? Predicate is a statement or sentence that contains variables. It will contain variables such that if you replace every value, if you replace every variable by specific value from their domain, then it will become true or false. This is the concept of predicate. Very simple concept. Like consider this predicate. On your screen you have another predicate. This is the predicate prime x. That means x is a prime number. This is not a proposition because it contains variables. So because of this variable, we cannot say it is true or we cannot say it is false, because the truth value will depend on this variable. Okay. So that is the reason this is not a proposition, because the truth value will depend on this variable. So this is the reason this is not a proposition. Now you can see that this is a predicate because it contains variables. Now if you replace this variable with a specific value, then it will become a proposition. Like this x, if I replace with 2, then you can see that 2 is a prime number, that is true. So you can see prime 2, that is true. Similarly prime 9, that is false because 9 is not a prime number. Okay, so you can see prime 2, if I replace this x with 2, then this will become true. This will become true proposition. And if I replace this x with 9, then that will become false proposition. So anyway, if you replace every variable if you replace by a specific value, then your predicate will become proposition. Now the next example you can see. Now you have two variables, c x comma y. Now you have two variables, total two variables you have. There is variable x, there is variable y. Now x is capital of y. Now you can easily see that, for example, I can say that C Jaipur comma Rajasthan. Okay, Jaipur is capital of Rajasthan. That will be true. Similarly, if I say that, for example, if I say Pune comma Maharashtra, that will be false because Pune is not a capital. Pune is not the capital of Maharashtra, so that will be false. So you can see in this predicate we only have one variable. In this predicate we have two variable. You can also have three variable. In this predicate we have three variable. There are total three variable. You can see that in this predicate e x y z, there are three variable x comma y comma z. Now you have to replace every variable by a specific value. Every variable, remember, every variable x y z, every variable you have to replace with a specific value. So tell me, what is e2 3 4 what is this? If I replace x with 2, y with 3, z with 5, if I do this, then what I will get? Tell me. E235, what is that? So you can see that will be true. And what is E4417? That will be false. So this idea, is this idea clear to everyone? Tell me, is this idea clear to everyone that in a predicate, this is actually important point. So that is the reason I am telling you this with multiple examples. So this predicate becomes proposition, correct? This predicate, it involves variables. There are variables in this. So it involves variables. Okay. So this predicate involves variables. Remember, this predicate becomes proposition. When it becomes proposition means either it will be true or it will be false. So this predicate becomes proposition. Proposition means true or false. So this so I can say this predicate, it becomes proposition when we replace every variable with a specific, with a value from the domain, Okay, remember different variables can have different domain. It is possible that different variables, they can have different domain. So finally this predicate will become proposition if you replace every variable with a value from the domain. Now, so this is the point. That is the reason this is also called propositional function. See, this predicate, this is also called propositional function. The another name of predicate is propositional function. Okay, why? What is the reason? Because you can see that it will become proposition when every variable is replaced by some value. So then it will become a proposition. So this predicate is also called propositional function. This is another name for predicate. Okay, now let's see. I want to tell you that these two important points about domain, you have to understand that domain in first order logic is never empty. Okay, so domain in first order logic is always non-empty unless I give you that it is empty. So for example, if I give you that domain is empty, then you have to consider domain to be empty. But if I don't give you any information about the domain, if there is no information about the domain, then remember by default, domain is always non-empty. Okay, please understand, this is very important point, that domain is always non-empty. In the first order logic, domain is always non-empty unless explicitly stated. If I tell you that domain is empty, then you have to consider domain to be empty. Other than that, always domain will be non-empty. Domain will have at least one element. The second point I want to tell you that, remember, different variables can have different domain, but by default, if no information is given to you about the domain, if nothing is mentioned about the domain, then all the variables, they have the same domain. Okay, in this situation you have to consider that every variable in the expression has the same domain. Domain of every variable is same. This is by default. Okay, remember, actually what happens, let me tell you what actually happens, that in the first order logic, when you write any expression, if I give you any expression, in the first order logic, if I give you this expression, for example, let's assume this is some expression I am giving you. Now, for this expression we have domain. This expression has domain. What it means? This expression has domain. What it means? It means that every variable in this expression has this domain. Okay, it means that it simply means every variable in this expression has domain D, refers to domain D. So this is something important, because sometimes you will make mistake if you don't consider this point. So remember, in the first order logic, whenever you write some first order logic expression you write, then this expression has a domain. It simply means that expression has a domain. It simply means that every variable in this expression has the domain D. So by default, you have to consider that they have the same domain if nothing is given. So domain of every variable is the same if no information about the domain of different variable. But if I tell you that domain of different variable is different, then you have to consider that. So in the question, if some other information is given to you, you have to consider that information. But if there is no information about the domain of different variable, this domain of different variable, if it is not given, then you have to consider that every variable has the same domain. Okay, and that will be called domain of this expression. So domain of expression means every variable in this expression has this domain. Now let's move on. Now the next concept we need to see is quantifiers. This concept we need to see. So we have seen two concepts so far. We have seen the concept of domain. This concept we have seen. Another concept we have seen is predicate. So these two concepts, are they clear? Please tell me. So these two concepts we have seen. Remember, this is a summary lecture. This is not a complete lecture. If you want to study first order logic in detail, with many questions, with many examples, if you want to study this first order logic or discrete mathematics, then you can study on the goclasses website. Just go to goclasses website and you will find discrete mathematics course that you can watch. So this is just a summary lecture. Quickly, I am telling you every important point about every topic in this first order logic. So we have seen this topic, all the important point about domain I told you, all the important point about predicate I told you. So these two topics are over. Now the next topic will be quantifier. What are these quantifiers? So quantifiers basically means, remember, if you see the English language, in the English language, these type of words are quantifier, like this word, few, all, many, some, any. Okay, this type of words, if you see, this type of words, they are quantification words. These words are called quantification words. Now, in the first order logic, the quantification words that we will use, these are all comma sum. So these are the two quantification words we have to see. So what I am just telling you that this type of statements are called quantified statements. This type of statements, look at this type of statements. These are called quantified. These are called quantified statements. Okay, so look at this type of statement, like some birds are angry, no one, any. So these type of words, if you see, some, no one, any, like this type of words, you can check this type of words, all, many, some, this type of words, if you notice, these words are called quantification words. The name of these words, they are called quantification words. But in the first order logic, we only study two quantified words. In the first order logic, we study two quantification words. We study two quantification words. Two quantification words are important, and these quantification words, what are they? One is one one quantification word is basically every, and the another quantification word is basically some. So every means for all. This is one quantification word, and some means for at least one. For at least one. So these are the quantification words that we study in the first order logic. Only these words, they matter to us. We don't care about these words, like this word we don't care, this word we don't care. So these words we don't care about. Okay, the only words that will matter to us, these are all comma some. These two words we care about. So these are the quantification words that we use in the first order logic, every comma some. Now let's see one by one. What is this statement? For example, if any time you want to write this, like for all x, for all values of x, if you want to like this, for all values of x, I can say p is true. For all values of x, px is true. If you want to write like this, if this is your English statement, please understand, this is an English statement. This statement is an English statement. This statement, if you want to write in first order logic, this is your English statement. This statement, if you want to write in first order logic, in the first order logic, then how will you write? Then you will write using this symbol. So for all values of x, see, for all means this, for all values of x. So you will write like this, for all values of x, this px is true. This px is true, you will write as px. So this is how you write. Okay, very simple point. What I'm telling you, that this, if you want to say in the English language, if you want to say this type of statement, like for all values of x, px is true, then how will you write? Then this is how you will write in the first order logic. You will say that, you can just simply say that for all x, this is the symbol. This symbol is called for all. The name of this symbol is basically for all, or you can say this name of this symbol is universal quantifier. This is called universal quantifier. Okay, this is the name of this symbol. This symbol has the name for all, or you can call it universal quantifier. So you can see, for all values of x, px is true. This is how you can write. Okay, very simple. So for example, let me give you example, like if you want to say that, consider this domain. Let me give you domain of x. The domain of x, let me give you like 2, 10, 12. Let's assume this is the domain. Now you want to say that, you can easily see that for all values of x, x is even, right? For all values of x, x is even. You can clearly see. For all values of x, because x can take only these values. Only these values can be taken by x. The domain of x is this. So the only these values x can take. X cannot take any other value. Now if you want to say that for all values of x, x is even, let me assume that this means ex. This is the predicate ex. Ex means x is even. Then how will you write it? You can write very easily. For all values of x, ex is true. Okay, so like this you can write. If you have any statement, you can write like this in the first order logic. Very simple. Now let's see when it will be true. So if I give you this statement in the first order logic, if I give you this expression, I give you for all x, px, and of course this x has a domain. Of course this x, remember this x has some domain. Okay, now You can easily see that, for example, the domain can be like this: a, b, c, d, and so on. Let's assume these are the domain. This domain can be finite or infinite. This domain, either this can be finite domain or this can be infinite domain, but this is definitely non-empty. I told you that domain is always non-empty, but non-empty. Okay, domain is always non-empty. This point I already told you, that unless I tell you that domain is empty, you always have to consider the domain is non-empty. So this domain can be finite, this can be infinite, but it is always non-empty. Now this is your statement for all x px. This is a statement. Now when it will be true, let's call it s. Let's call it s. Now you can notice s is true. When it will be true? Tell me when it will be true. This is saying that for every value of x, px is true. This is saying, this statement s is saying that for every value of x, px is true. So you can see this will be true if for every value p will be true. Okay, so this will be true if and only if for every value x can take, for every value in domain of x, for every value of x. Okay, what I am saying that for every value of x in domain of x, px is true. Okay, then it will be true. Very simple. And when it will be false? When it will be false, like I can say this s, this statement s, this will be false if for at least one value, for at least one value, for some value, for at least one value of x, this px is false. For at least one value, this px will be false. Then I can say this will be false. So this is your universal quantifier. Consider this example on your screen. Let's consider this. Consider this example. Now, so you can see that your domain is these faces on your screen. These faces are the domain. So now you tell me, this is true or false? For all x smiling x, is this true or false? This is the domain. Assume that this is the domain. These people are the domain. Now, if these people are the domain of x, for variable x, these people are the domain of x. Now you tell me, is this statement true or false? Yes, of course, this statement is true, because you can see this statement is saying that everyone is smiling. This statement is saying that for everyone they are smiling. For every value of x is smiling. Okay, for every value of x that is smiling. So you can see, yes, smiling. So everyone is smiling. So I can say this will be true. Very simple. You can notice smiling, he is smiling. Okay, this is also smiling. So all of them are smiling. You can check all of them. So finally I can say that because everyone is smiling, for every choice of x, this is true. Okay, for every choice of x, this smiling x is true. This is true. So I can say finally that this statement will be true. This is going to be true. So very simple. Now let's see this example. What about this one? Is this true or false? If your domain is this is the domain of x. X can take these values. This is the domain. X can take any of these values. This is the domain of x. Now you tell me this statement is true or false. Now this statement is saying that everyone is smiling. This statement, look at this statement. This is saying that for every x it is smiling. For every choice of x it is smiling. So you can see, for every choice of x, is it smiling? No, this person is not smiling. So you can definitely say that because of this one person, this has become false. So this statement has become false. I can say this is a false. So like this you can do these questions, you can very easily do. So did you understand this universal quantification? Universal quantification of px, did you understand? If you want to say px is true for all values of x in the domain of x, then you can write like this: for all x px, it means for every x px is true. Okay, for every x px is true. So this is how you can read. Now let's move on. So this is called universal quantifier. Now consider this and tell me the answer. This one, tell me the answer for this one on your screen. What is the answer for this one? Is this true or false? I am asking this is true or false. Look at this and tell me, is this true or false? What is the truth value? I am asking for the truth value. This is a question. What is the truth value? Tell me. So you can easily see that there are two situations here. There are two sentences here. This is, you can see, this is the you can clearly see this is the open parenthesis, this is the close parenthesis. So let's call it alpha. Let me call it alpha, and let me call it beta. So there are two sentences here. You can see this is basically alpha implies beta. Ultimately, this is alpha implies beta. You tell me about alpha. Is this true or false? This alpha, is this true or false? Look at this alpha only. Forget about beta. Forget about beta. You tell me about alpha. Forget about beta. You tell me alpha. Is this alpha true or false? Can I say everyone is smiling? Alpha is saying that everyone is smiling. For every choice of x, it is smiling. Every value of x is smiling. Can I say? No, this is not, like, you can clearly see that this person is not smiling. Okay, this person is not smiling. These are not smiling. So definitely I can say alpha will be false. Now it does not matter what is beta. Correct? You can see now it does not matter what is beta. False implies anything. But actually you can check it out. This beta is what? Tell me what is this beta? Now don't worry about alpha. Forget about alpha. Tell me what is beta. Beta is saying that for every choice of y, it is wearing a hat. Remember x, y, they have the same domain. This domain, this is the same domain x has, this is the same domain y has. Why? I told you very important point that if no information is given about domain of different variable, if they do not tell you that different variable have different domain, if they do not give you that information, then you have to consider that all the variables have the same domain. So the variable x also has this domain, and variable y also has this domain. Both the variables have this same domain. So now you tell me, what is the truth value of this beta? This beta is saying that for every choice of y, for every value of y in the domain of y, in this domain, for every value of y, it is wearing a hat. Yes, this is true. Yes, this is true. So you can notice what is false implies true. What is false implies true. Ultimately, that is true. So you can notice this statement is basically true. Is this clear to everyone? Please tell me. Is this understood? This point you have to understand. Again, I am telling you that in first order logic, domain of every variable is same. Domain of every variable is the same. Every variable is the same unless explicitly given different. Unless they tell you, unless explicitly stated different. Okay, so if no information is given, or I can say, so then you have to consider domain of every variable, this domain you have to consider same. Okay, unless they give you explicitly, they tell you that it is different. So very simple, you can see. Please understand, this is a very simple question. Here you have, this is your alpha, this is your beta. So all you have to do, just check what is the truth value of alpha. Alpha is false, beta is true. False implies true, that is true. False implies true, that is true. So like that you can do. Now, one more thing I want to tell you, if your domain is empty, let's consider that domain is empty. If this domain of x, and if this is finite, if this is finite, okay, if this domain, I am telling you, if this domain is finite, for example, let's assume the domain is like a, b, c, d. If this is the domain, now what is this statement? For all x px. If domain is finite, then what is this statement saying? Tell me what this statement is saying. If domain is finite, let's assume this is the domain a, b, c, d. This is the domain. This is a finite domain. There are 4 elements in this domain. Now tell me what this statement says. This statement on your screen, for all x px, it says that for every value of x, p is true. For every value of x, p is true. This is the value of x, like this is the domain of x. So you can see this is the domain of x. For every value of x, p is true. It means pa is true, and pb is true, and pc is true, and pd is true. Okay, so you can see that if your domain is finite, then your universal quantifier is basically nothing but conjunction. Your universal quantifier is nothing but conjunction if domain is finite. So this is something important. Like if domain is finite, if I say that domain is finite, then this universal quantifier is just a conjunction of all these elements. You can see for all x px, this is just conjunction of pa, pb, pa and pb and pc and pd. Okay, so like that. Now let's see the next. The next quantifier is existential quantifier. The next quantifier says that what this says, there exists x px. This is another quantifier. This is called existential quantifier. The name of this symbol is existential quantifier, or you can call it there exist. You can read it there exist, or you can say for some. All these things are same, or you can say for at least one. For at least one. So all these things are same. Please understand. This you can read like this. This you can read like this. Now, what I'm saying, this says that there exists for some value of x, p is true. What it says that for some value, I can say it says that for some value, some means at least one. Some means at least one. So for some value of x, for some value of x in domain of x, for some value of x in domain of x, px is true. This is what this says. Okay, this is your existential quantifier. There exists x px. It means that for some value, there exists a value for which this px is true. Very simple. So you can see there exists x, some formula. You can have some formula. Then in this situation, when it will be true, when this will be true, this will be true if for some choice of x from the domain of x, of course. So for some choice of x, this becomes true. This becomes true for some choice of x. Like for example, you can see this is true. Why? Because for some choice of x, it is true. You can see for x equal to 2, if you take x equal to 2, this will be true, this will be true. So for some element, this is true. Okay, there is some element for which this is true, and that is the reason this complete expression is also true. So you can see, if I give you this statement, there exists x px, and there is a domain of x, of course. So let's assume there is a domain of x. This is the domain of x. Then all you have to check, and so on. This is your domain. Now, what you have to do if s is true? So you can say s is true. All you have to do this. S is true if and only if you have to find some value for which this px is true. Okay. So this s will be true. This expression s, this will be true if and only if for some value in this d. Okay. For at least one value in d. For at least one value in d, this px must be true. This px must be true for at least one value. All you have to do is just find one value. Just give me one value, nothing else. I don't want more. Just give me one value. Now, if you cannot give me any value, then this will be false. If you cannot give me any value, like if I can say for all elements in D, if this is false, then I can say it will be false. Okay, so this is the idea. Very simple. So this is existential quantifier. It says that for at least one person in this domain, this px must be true. Okay, let's take example. Consider this. Is this true or false? Tell me. Is this true or false? Tell me about this one. So this is your, again, existential quantifier. Is this statement true or false? This is saying that for someone is smiling, at least one person is smiling. This is the domain of x. This is the domain of x. Now I am saying that at least one person is smiling. There is at least one person which is smiling, and this is the domain of x. The x can take any of these values. This is the domain. Now you tell me. Now what this statement is saying, look at this statement. This statement is saying that at least one person, at least one value of x is smiling. At least one value of x, it is smiling. So you can see, yes, at least one person is smiling. Then yes, it will be true. So you can clearly see this is smiling, and it is enough. This person is enough. I don't care about the remaining people. I don't care. I only care about this person. It is enough. So because this person is smiling, at least one person is smiling. So I can say this statement becomes true because at least one person is smiling. Okay, so I can say this will be true. Now let's move on. You tell me about this one. What is the truth value of this one? At least one person is smiling, but you can notice no one is smiling, right? There is no one who is smiling. For everyone, this smile is false. I can say for everyone in this domain, this smiling, this is a false. So there is no one who is smiling, so I can say this will be false. So this statement will be false. Now let's move on. So this is clear to everyone. What is existential quantification? Existential quantification means there exists an element in the there is at least one element for which this px is true. For at least one person, this px must be true. Let's consider the next. Also remember, all these things are same. For all x px, there is at least one x for which px is true. There exists x for which px is true. All these things are basically same. You can read it in many ways. You can see for some, for at least one, there is, all these words are same. And similarly this, there exist. All these four words, they are same. Now let's see. Now you tell me, if the domain is finite, then what will happen? If a domain is finite, then what will happen? If I give you, if domain of x that is finite, if I give you a finite domain, like for example a, b, c, d, if I give you this domain, in the domain you have 4 elements, then you can see this statement. What this statement says? This statement says that at least one value of x, this for at least one value of x, this px is true. So pa is true, or pb is true, or pc is true, or pd is true. Correct? So you can see either pa must be true, for either for this p must be true, or for this p must be true, or for this p must be true, or for this p must be true. So you can see this statement, for all there exists x px, this is basically nothing but disjunction of all these individual elements. Okay, so like this you can see, very simple. So if your domain is finite, then this existential quantifier is simply disjunction of all the elements. This, there exists x px, this is nothing but either for this element it will be true, or for this element, or for this element. For at least one element it should be true. Okay, let's move on. You tell me the answer for this question. A question I have taken for you. You tell me what is the truth value of this and what is the truth value of this. Quickly tell me what is the answer. What is the truth value of these two? Tell me quickly. So you can see, suppose px is the predicate, this is the predicate, it is px. Suppose this is your px, this is the px. The universe of x is a 1, 2, 3. This is the universe. X can take only these values. X can take either this value or this value or this value. This is the domain of x. Now you tell me what this statement is saying. This is saying for everyone p is true. Means for this p is true, for this p is true, for this p is true. For everyone p is true. But you can see that for everyone p is not true, right? For x equal to 1, this is false. So definitely this will be false. Correct? This is going to be false. Why this is going to be false? Because at least one person is enough to make it false. Because you cannot, this is saying for everyone p must be true. This is what, okay, so this expression is saying for everyone, for every value of x, px must be true. But you can notice this is not true. You can clearly see that p1, that will be false. P1 will be false. So definitely this also will be false, because at least one person is enough to make it false. Okay. Now what about this one? There exists x px. So this statement is true because you can clearly see for at least one person. Like for this person, p2 is actually true. So this is actually true. So one person is enough to make it true and one person is enough to make it false. Let's move on now. Let's see this question. Tell me the answer. Tell me the answer quickly. What is the answer for this question? The statement is saying that let p and m, this is a predicate. This is a predicate which is mn greater than 0. So this predicate is given to you. The domain for m comma n is set of integers. This domain is given to you, set of integers. Which of the following statement is true? Two statements are given to you. First of all, look at this statement. What this statement is telling you? This is simple. This is simple predicate. You are replacing this n you are replacing with remember, this n you are replacing with the 3 minus 3, and this m you are replacing, with 2. Okay, so this is the simple point. You can notice this will be basically mn greater than 0. Okay, so this is definitely false. This is definitely false. Okay, what about this? So this is actually false. This is definitely not true. What about this one? Look at this one. What this statement is saying? This statement is saying that for all m, what is true? This is saying for all m, this is true. For every value of m, what is true? You can see n is 0. So for every value, it is saying that 0 is greater than 0. For every integer, can I say 0 is greater than 0? Tell me. Can I say for every integer 0 is greater than 0? For every integer, can I say 0 is greater than 0? This is definitely false, because this 0 greater than 0, this itself is false. This itself is false. So for everyone, this is false. So ultimately, this will be false. So this is also false. What about this one? What about this? This is saying that there exists n such that minus 3n that is greater than 0. There exists n. Remember, the domain of n is set of integers. This is the domain for n. So you tell me, the question is saying for some value of n, there exists n. For some value, this is true. This is true for some value. Yes, definitely. For example, so this is actually true. Why this is true? Because you can easily see that, okay, for what is the witness? It is called witness, like for whom this is true. For whom, for this, what is the witness? For this minus 3 greater than 0, for this, who is the witness? Who will make it true? You can notice n equal to minus 2 will make it true. So one value is enough. So this is definitely true. So the third one is true. The remaining are not true. Is this clear to everyone? Let me know. Okay, very simple. Now let's move on. Now let's see this question. Tell me the answer for this one. What is the answer for this one? The existential quantifier. This statement is given to you. Now let's look at this statement. First of all, you can see that this parenthesis is going from here to here. This is the parenthesis. So let me call it alpha. And this parenthesis is going from here to here. Let me call it beta. So you have alpha implies beta. This alpha implies beta you have. You tell me, what is alpha? What is alpha? Is this true or false? Look at this alpha and tell me, is this true or false? Forget about beta. Forget about this beta. You tell me, this alpha, is this true or false? Someone is smiling. Yes, of course, this person is smiling. You can notice someone is smiling. So this alpha is definitely true. So I can say this, this alpha is basically true. What about this beta? What about this beta? Beta is saying that, now forget about this alpha. What about beta? Someone is wearing a hat. There is someone, there is at least one person who is wearing a hat. No one is wearing a hat, right? There is no one who is wearing a hat. So this is definitely false. What is true implies false? True implies false. That is a false. Correct? True implies false. That is false. So ultimately I can say this is a false. So this statement is false. I hope this is clear to everyone. Now let's move on. Now, something very important I want to tell you. This is something very important. So you tell me when this will be false. Like if I give you, for consider this statement S, which is for all x px. You tell me when this will be true. When this will be true. When this is going to be true. This is going to be true. When this is going to be true. True if and only if. When this will be true, you tell me. Let's assume the domain. There is a domain of x. So let's assume the domain of x is D. Let me assume domain of x is D. This D is the domain of x. Now you tell me when this will be true. This statement, for all x px, for every value of x, this p must be true. So you can notice this will be true if for every value of x, in domain of x, p must be true. This is true. So then it will be true. Now you tell me when it will be false. When it will be false. This will be false. When it will be false. This will be false if and only if one person is enough to make it false. Correct? See, everyone need to make it true. If this want to be true, if you want to make it true, then then everyone in everyone in the domain of X must make it true. Okay, everyone should make it true. But remember, if you want to make it false, one person is enough. So this will be false if and only if for at least one person, for at least one value. Okay, for at least one value of X in D, this Px is false. Okay, for at least one value this must be false. Remember, one person is enough to make it false. This one person will be called counter example. This one person you will call counter example because it is making false. Is this clear? Please tell me, is this clear to everyone? Because one person is enough to make it false. At least one value, one person is enough to make it false. One person. If you want to make it true, everyone should make it true. For every value of X in this domain, this P must be true. But you can notice, if you want to make it false, one person is enough. For at least one value, this Px must be false. So this is called counter example because it is making it false. Now the second, look at this one. If I write this, there exists X. Now what will happen? Now when can you say it will be true? Now you can notice it will be true. It will be true. When it will be true? It will be true if for at least one value of X, this Px must be true. Okay, for at least one value of X. For at least one value of X, this Px must be true. So one person is enough to make it true. Agree? Do you agree that one person, one element in this D, in this domain, one element is enough to make it true? So that element we will call witness. We will call that element witness because one element is enough to make it true. To make it true, one element is enough. We will call that element witness. Now, when can I say this will be false? This will be false if everyone is making it false. Okay, if everyone is making it false, so I can say if for every value this Px is false. So very simple. So remember, this is false. To make it false, one person is enough. To make it true, one person is enough. So very simple. So finally you can see this for all X. And what about this one? Like if I give you this one, there exists X negation Px. What about this? There exists X, this negation Px. Now you tell me. So you can clearly see this will be true if for at least one person this is true. For at least one element this is true. Means for at least one element P must be false. Okay. So you can easily see that for at least one element P must be false. So this will be, look at this statement. When this will be true? This will be true if for at least one element this must be true. And if this negation is true, it means Px is false. So I can say this will be true. This expression will be true if for at least one person P is false. For at least one person P is false. Okay, for at least one person. Now similarly you can notice when this will be false. This will be false if for everyone this is false. For everyone this is false. It means for everyone P is true. For everyone P is true. Similarly you can check this one. For all X negation Px. When it will be true? It will be true when for everyone this is true. It means for everyone Px must be false. For everyone this Px must be false. And similarly when this will be false? This will be false if for someone this must be false. For at least one person this must be false. It means for someone this P must be true. For someone this P must be true. So like this you can check it out. Is this table clear to everyone? Please tell me. Let me know. A beautiful question can be created in the GATE exam because like this. So you can see that, you can see when this will be false. This will be false if for someone, see this will be false. This will be false if for someone P is false. Similarly, this will be false if for everyone P is false. Similarly, this will be false if for someone this is false, or I can say for someone P is true. For someone P is true. Similarly, this will be false if for everyone this is a false. Means for everyone P is true. For everyone P is true. So is this table clear to everyone? Please tell me. Some very nice questions can be created from this table. Let me know. Is this table crystal clear to everyone? Is this understood to everyone? Let me know, because this is very important table. In the GATE exam, they can ask you some beautiful questions on this table. These are the, I can say, this is a MSQ question can be created on this, from this table. So this is very important to understand. Now let's move on. Now let's see. So these points, all these points we have seen. Now let's see this question. Consider this question on your screen. So tell me, what is the truth value here? What is the truth value of this? Px is given to you, x is prime. Qx is given to you, x is even. The domain is given to you. This is the domain. 2, 4, 9. This is the domain. Domain is already given to you. Now you tell me, what is the truth value here and what is the truth value here? What is the truth value here and what is the truth value here and what is the truth value here? This is the question I want to ask you. So tell me, for all x px, remember the domain is 2, 4, 9. Can I say for everyone it is prime? Can I say everyone is prime? No. You can see 4 is not prime, 9 is not prime. So definitely this will be false. Definitely this is going to be false. Okay. This is definitely going to be false. You can easily see. Now what about the next one? Now what about this one? For everyone q is true. For every value of x, this q is true. Means everyone is even. That is also false, because this 9 is not even. So definitely this is also false. Okay, what about this one? For all x, px implies qx. See, you can see that for all x, px implies qx. Remember, for this universal quantifier, this is the scope. This is the scope. For this universal quantifier, this is the scope, because we are this parenthesis is telling you the scope. From this parenthesis to this parenthesis, this is the scope of this universal quantifier. So please understand this difference between these two. I want to tell you this difference is very important. So let me tell you. In this situation, what will happen? Because this is the scope. So if I give you, let's assume x is 1, 2, then what will happen here? Then this statement is same as, you can think like this. This statement is basically this and this. Okay. So what and what? You can see. Remember, this is the scope for this universal quantifier. For this universal quantifier, this is the scope. So it means this x and these x are same. They are the same x. These two x, they are same. So it means when you put x equal to 1, you will put like this. When you put x equal to 1, you will do like this. When you put x equal to 2, you will do like this. Okay. Remember, you cannot do this. Please understand that you cannot do this. If you do this, then that will be wrong. If you do, for example, P1 implies Q2. Like this x you replace by 1 and this x you replace by 2. If you do this, that will be wrong. The reason is very simple, that this is the scope of this universal quantifier. For this quantifier, this is the scope. It means that this x and this x are same. Please understand. These two x, they are basically same x. So you cannot do this. So this is wrong if you do this. Like if you do that P2 implies Q1. If you do this, that will be wrong. So this is completely wrong. Okay, this is completely wrong. So you cannot do this. This is what I'm telling you. So this you cannot do. This you cannot do. Okay. Now let's see the next scenario. The next scenario is this. If I give you S is like this. For all x px and for all x qx. Now you can see that for this universal quantifier, only this is the scope. And for this universal quantifier, only this is the scope. Now remember, these two x are different. Please understand, this x has nothing to do with this x. They are completely independent. They have nothing to do with each other. For example, you can say in this area, this is the zone. And in this another area, this is the zone. These two zones are not same. Correct? Okay, in this area in Rajasthan, this is, let's assume this is Deepak in Rajasthan, and let's assume this is maybe in Tamil Nadu this is some Deepak. So you can see that they are not same. So please understand, this x and this x, they are different because this is the scope of this universal quantifier and this is the scope of this universal quantifier. So they are completely independent of each other. They have nothing in common. So if you are confused, you can write it like this. If you are confused, then you can write like this, that for all x px, and what you can say, for all y py. So if you are confused, so remember, this x has nothing to do with this x. They have nothing to do with each other. But here you can see the scope of this universal quantifier is this one. This is the scope. You can check, this is the scope. So these two x are basically same. They will always take same value. Either both will be 1 or both will be 0. Or both will be 2. So they will always take the same value. I hope this point is understood. Now let's see this question. So what about this one? For all px implies qx. So this is, you can see, this is the scope of this universal quantifier. For this universal quantifier, this is the scope. Now what you will do? What you are going to do here? So if I do this, for all x, px implies qx. For everyone, you are going to check this. And you know that x, domain of x is 239, 249. This is the domain of x. Now for every element, you are going to check this. Please understand. For every element, for this element, what is this? For this element, what will be this one? Let me know. For 2, if you place 2 here, p2 implies q2. Remember, p2 means 2 is prime. q2 means 2 is even. Yes, both are true. So for this 2, this will be true. Okay, what about this? What about this 4? What about this 4? So you can notice this will be 4 is prime, that is false. 4 is prime, that is false. False implies true, that is true. So for this also it will be true. And what about this one? What about this one? So you can see 9 is not prime, so this will be false. 9 is not even, so this is also false. So you can see that definitely it will be false implies false. This is also true. So for everyone this is true, right? Correct? Look at this box. You can consider this as a box. This you can consider as a box. Now you tell me, this box, you can see this box is true for every value of x. For every value of x, this box is true. So this universal quantifier also becomes a true. Okay, so this universal quantifier, this becomes true. I hope this point is clear. Let me know. Is this understood? Is this understood to everyone? So very simple. Now you can see that this will be false, and this will be true. Okay, let's move on now. So similarly, let's see this question. You tell me the answer for this. Tell me the answer for these questions. So you can see, we are saying px is x greater than 2. This is px. But we are not using px. In these expressions, we are not using the px. The domain of every variable, the domain of x is n. Set of natural number means 1, 2, 3 and so on. This is infinite domain for x. Now you can easily see that, see, this does not depend on the x, right? Correct? If you look at this does not depend on the quantifier. It is just simply true. So automatically I can say that this also will be true, because this quantifier does not affect this. Okay, this quantifier, this existential quantifier does not affect this expression. So I can simply say that for someone this is true. Of course it is always true, right? This is always true. So ultimately this also will be true. Ultimately your answer is going to be true. Similarly, what about this one? This is false. For everyone this is false. So again you can notice your answer is going to be false for existential quantifier also. And similarly you can notice this is a false. So again for this universal quantifier also the answer will be false. Can you notice one thing? So simple observation you make. That simple observation is this, that if your internal expression is not dependent, like if I write like this, for example, this for all x, and if this is independent of x, if this expression is independent of x, let's assume if this expression, let's assume you have this expression, some expression e you have, and this expression e is independent of x. If this is independent of x, then this whole expression will be same as what? If this e is independent of x, remember, this e does not depend on x. Please understand. Or I can say e, okay, yeah, okay, so very simple. You can see e is independent of x. Then for all x e, that will be same as e, correct? Because this universal quantifier, this quantifier cannot affect this e. Similarly, this e, this is also same as e. Very similarly, you can do this. So I hope this is clear to everyone. So remember, if this expression e is independent of x, then these quantifiers cannot affect the truth value. These quantifiers you can remove, very simple. These quantifiers you can simply remove. The truth value will not change. So this is something important. If this e is independent of x, if this does not depend on x, then you this universal quantifier of x, this existential quantifier of x, they cannot change the value, they cannot affect the truth value of e. So that will be same as e. Now let's see this. If the domain, if the domain is empty, remember the domain you never have to take an empty. I told you, never take domain to be empty. But if the domain is given to be empty, if they tell you that domain is empty, then what will happen? If this domain is already empty, like if this x, okay, this x, this is, let's assume this is referring to empty domain. If the domain of this element x is empty, then what will be the truth value of for all x px? What is going to be the truth value of this? In this situation, remember, for all x px, it will be always true. So when domain is empty, this statement, this is always true. And when domain is empty, this statement is always false. So this is the special case when domain is empty. If your domain is empty, then this statement is always true and this statement is always false. The reason is very simple. What is the reason? See, if you want to make it true, you need at least one witness, correct? Agree or not? If you want to make it true, you need at least one witness. At least one witness you need. Because there is no witness, so this is a false. Similarly, to make it false, you need one counterexample. If you want to make it false, you need some counterexample you need, but there is no counterexample, so this is true. So I hope this point is clear that if domain is empty, then this will be true and this will be false. Very simple point. So remember this point, that this universal quantified statement is true unless there is a counterexample. It is always true unless there is a counterexample. You need a counterexample to make it false. Similarly, this existential quantified statement is false unless there is a witness. You need a witness. You need a witness if you want to make it true. So to make it true, you need a witness. To make it false, you need a counterexample. Because there is no witness, there is no counterexample. So this will be true, this will be false. A very simple point. Now let's move on. Like consider this example. Can I say someone is smiling? In this empty room, if I say someone is smiling, then definitely that is a horror movie, right? Yes or no? Like in this is an empty room. In this empty room, if I say someone is smiling, then what you will think? You will think, okay, definitely you will say no one is smiling because there is no one in this room. In this room there is no one, so definitely it should be false. So remember, when you have empty room and you say that someone is smiling, that is a haunted movie, and that is the reason you can easily see that this is a false. Now, the reason is very simple, because no one can make it true. There is no one here who can make it true. There is no witness to make it true. So that is the reason this is false. Similarly, if this is your empty room and you say everyone is smiling, this is true because you need a counterexample to make it false. Okay, so you cannot make it false because your room is empty. There is no counterexample. So this is taken to be true. Okay, let's move on now. Now we will see how to convert English to first order logic and first order logic to English. Let's see this one. This is very important from the GATE exam point of view. So let's see this. Now some statements, some type of statements are frequently used. So let's see those statements. So for example, this one, look at this statement. Some happy person wears a hat. How to convert this? Happy X, this is a predicate. Some predicates are already given to you. Happy X is a predicate, which means X is happy. So this is a predicate. Happy X, it means X is happy. Okay. Wearing hat X, it means X is wearing hat. So these two predicates are already given to you. Two predicates we have. Now write a sentence in first order logic that says some happy person. This is some happy person. Please understand, this is existential quantifier. Some happy person wears a hat. So how to do this? How to do this? Now you might be thinking that there are two choices. See, if I say that some A is B, some A is B. So how to write it? Should I write like this? There exists X. If it is A, it is B. Someone, if it is A, it is B. Someone, if it is A, it is B. Someone. And another is someone, it is A also and it is B also. Which of them is correct? Tell me, which of them is correct? So the answer is this is not correct, this is correct. Okay. So when you have this type of statement, some A is B, this statement is written like this, that some A is B. There is someone who is A and B. There is someone who is A and B. This is how we write. Very easily you can see. For example, look at this one. Look at this diagram. In this diagram, you tell me, some happy person is wearing a hat. Is this true? This English statement, is this true? Tell me. From this diagram you see and tell me, is this English statement true or false? Some happy person is wearing a hat. Some happy person is wearing a hat. So this is false, right? See, some happy person is wearing a hat. No happy person is wearing a hat. So definitely this is false. Do you agree this is false? Do you agree this is false? Okay, what about this statement on your screen? What about this? There exists X. There is someone who is happy and who is wearing a hat. There is someone for which this is true. So you can notice there is no one, right? So there is someone for which this is true, this is true. You can notice there is no one for which both of them are true. Correct? These two are not true for anyone. There is no one for which both of them are true. So this is also false. This is false. This English statement is false. What about this last statement? What about this last one? So you can notice they are false. Both of them are false. What about this last statement? This is saying that for someone this must be true. For someone this must be true. You can check that. For this person, look at this person. For this person this will be true, right? Do you agree? Do you agree for this person this will be true? Because he is not happy. So false implies anything that is true. Okay. For this person, for this element, for this value of X, you can see happy. This is false. False implies anything is true. So you can clearly see that this will be true. Okay. So this will be true because of these people. So now you tell me which of them are correct. This is your English statement. For this English statement, this conversion is correct or this conversion correct? Which conversion is correct for this English statement? An English statement is given to you. For this statement, which conversion is correct? You can see English statement is false, but this is true. But this is true. So definitely this is not a correct. This is not a right conversion. This is not a correct conversion. So finally your answer will be this one. So I just want to tell you that if you have this statement, some P is Q, then you will write it as there exists P, there exists X, which is P and Q. Okay. Now the next point. So this is very useful. Remember, this is a useful intuition. You can see that this existential quantifier. Okay. So like this. Now let's see the next. What about this one? Every happy person wears a hat. If I give you this statement that every A is B, how to write it? How to write this statement? Every A is B. Every A is B. So should I say that everyone is A and B? Should I say this or should I say this? If it is A, it is B. If it is A, for everyone, if it is A, it is B. So tell me what is correct. Let me know. Which of them is correct? Please tell me. So you can see that very easily you can see. We are saying that every A is B. We are not saying that everyone is A and B. See, this statement, look at this statement. This is saying that everyone is A and B. Everyone is both of them. But what we are saying that every A is B. Okay. So you can see, we are saying that for everyone, if you are A, then you are B. If X is A, then X is B. So this is correct. This is not correct. Now let's move on. So you can easily see that, for example, consider this photo, consider this domain. This English statement, is this true or false? Every happy person is wearing a hat. Look at the happy people. Are they wearing hat? Look at happy people. Look at happy people. Yes, they are wearing hat. Every happy people, every happy person is wearing hat. That is true. Okay. Now you tell me these two statements, which of them are true, which of them is false? On your screen, these two statements. Can I say everyone is happy and everyone is wearing hat? Can I say that for everyone this is a true? Definitely not. For this person, this is not true. This is not true for this person. So definitely I can say that this is false. It will be false. Okay. Now you tell me about this one. Can I say for everyone this is true? Can I say that for everyone, if it is happy, then it is wearing a hat? Yes, you can see that if it is happy, it is wearing a hat. If it is happy, wearing a hat. If it is happy, it is wearing a hat. So you can see for every element, whatever element you take, this will be true. You can see for this element it is true because it is not happy. It is not happy. So false implies this, that will be true. For this, so you can notice for this also this will be true. For this also this will be true. For this also this will be true. For this also it is true. For this also it is true. So you can easily see that this statement is true. So finally, your English statement is true. The middle statement is false. The last statement is true. So definitely middle statement is not correct. I can say this middle statement, this is definitely not correct. So if you have all P's or Q's, then how will you write? You will say for every X, if it is P, it is Q. So this is how to write it. Okay, very simple. So remember, this point is very important, that this universal quantifier, it is usually paired with implication. This universal quantifier, it is usually paired with implication. This existential quantifier, it is usually paired with conjunction. Okay. So with this universal quantifier, we most of the time we use this implication, and with this existential quantifier, most of the time we use conjunction. So this is how we write. What is the translation of these statements? Let me know. Now the question is given to you. Rx is X is rabbit. What is this Rx? Rx is X is rabbit, and Hx is X hops. Domain is a set of all animals. Domain is set of all animals. Every animal is in the domain. So now you tell me, what will be this statement A? Look at this statement A. This statement A is saying that for everyone, if it is rabbit, then it is hopping. For every animal, we are saying that if it is rabbit, remember the domain is animals. Please understand, the domain is all animals. This is the domain. Domain is set of all animals. Now you tell me one by one. So what this statement is telling you? This is telling you that for every animal, if it is rabbit, then it is hopping. Okay, we can say for every animal. This is what you can say. You can say for every animal. Okay, so this means this. For every animal. If it is rabbit, for every animal we are saying that if you are rabbit, then it hops. Okay. So it simply means that every rabbit hops, because we are saying if you are rabbit, you will hop. If you are rabbit, you are hopping. You hop. Okay. So you can see that in simple words, I can say that every rabbit hops. In simple words, I can just simply say that every rabbit hops. This is how you can write. Now let's see the next statement. So this means every rabbit hops. What is the next? For all X, Rx and Hx. What this means? For all X. This is option B. For every animal, we are saying that you are rabbit and you are hopping. Okay, for every animal, we are saying. What we are saying to every animal? To every animal, what we are saying? We are saying that it is, for every animal, it is rabbit and it hops. Okay. So in simple words, I can say that everything is rabbit and everything hops. Correct or not? In simple words, I can say every animal is rabbit. In simple words, I can say every animal is rabbit. In this jungle, every animal is rabbit and hops. Okay? Every animal that is rabbit and it hops. In simple words, you can write like this. What is the next? What is the next? There exists X. If it is rabbit, it hops. So the statement number 3. Statement number C, what is that? That is there exists X. If it is rabbit, it hops. Now you tell me about this one. We are saying there is someone. See, the best way to write this is there is someone. If it is rabbit, it hops. Remember, there is someone. If it is rabbit, it hops. If it is rabbit, it hops. If you want to understand this, then you can write like this. You can write like this, that there is someone such that either it is not a rabbit or it hops. Like this you can understand. Please understand that alpha implies beta, that is same as alpha dash or beta. So you can write like this. Now you can understand. We are saying there is someone, either it is not a rabbit or it hops. So I can say there is some animal. There is at least one animal which is which hops or not a rabbit, which is either a rabbit, which is either not a rabbit, which is either not a rabbit or hops. Okay, is this clear to everyone? Please tell me what this statement is saying. This statement is saying that there is some X, there is some animal which is either not a rabbit, either it is not a rabbit or it hops. So there is some animal, there is at least one animal, either it is not a rabbit or it hops. This type of animal is there. This type of animal is there which is either not a rabbit or it hops. So this is your statement C. What is statement D? Let's see the statement D. The statement D is there exists X. What this says? This says that there is some animal which is rabbit and hops. Okay, so it simply means there is some animal. There is some animal. There is some animal which is rabbit and hops. There is some animal which is rabbit and hops. It simply means that some rabbit hops. In simple words, I can say there is some rabbit which hops. So some rabbit hops. In simple words, I can say like this. I hope all of them are clear. Okay, so here we are saying that some rabbit hops. And here, please understand, here we are saying that there is some animal, either it is not a rabbit or it hops. The difference you can understand between C and D. Look at this. If I give you this situation, that consider that these are the rabbits. Let's assume this is a rabbit and it hops. This is a rabbit. Let's assume it does not hop. It does not hop. And let's assume this is a tiger. And let's assume it hops. And let's assume there is a lion. It does not hop. Okay. So consider this situation. Now you can see what will be truth value of C and what will be truth value of D. Can anyone tell me? In this situation, please consider this situation. This is your domain. In the domain, you have 3 elements. And I am telling you that this is a rabbit which does not hop. This is a tiger which hops. And this is a rabbit. This is a tiger. This is a lion. So you tell me now, what will be the truth value of C? This C is saying that there is some animal, either it is not a rabbit or it hops. So C will be true. C will be true because there is some animal which is not a rabbit. There is some animal which is not a rabbit or it hops. So C is true because of lion. C is true because of tiger. C is true because tiger hops. So you can notice this C will be true. There is some animal which is either not a rabbit or it hops. So this C will be true. What about D? D is saying that there is some animal which is rabbit and it hops. This is option D. This is saying some animal is rabbit and it hops. You can notice there is no element, there is no animal which is rabbit as well as hops. Like this is a rabbit but it does not hop. This hops but it is not a rabbit. So you can notice this is a false. This option D is false. Okay. Is this clear to everyone? So very simple. Now let's move on. So let's see these four statements, how to write them. All P's are Q's. How to write it? You write it as for everyone. If it is P, then it is Q. Okay. For everyone, if it is P, then it is Q. Some P's are Q's. It means there is someone. It is P also. It is Q also. It is P also and it is Q also. How to write this? No P's are Q's. Okay. No P's are Q's. I can say for everyone, if it is P, it is not Q. For everyone, if it is P, it is not Q. If it is P, it is not Q. So I can say no P's are Q's. It means for everyone, if it is P, it is not Q. The same thing you can also write contrapositive. If it is Q, it is not P. Like this also you can write in the contrapositive way. Okay, let's see this. Some P's are not Q's. So there are some P's which are not Q. There is something which is P and not Q. So like this you can write. Okay, so this is the these are all these statements. Are they clear? Please tell me. All of them, are they clear? Now let's see the next. The next concept is nested quantifier. How can we do the quantification, nesting quantification? So nested quantifier means one quantifier is in the scope of other quantifier. Two quantifiers are nested. When can you say they are nested? They are nested if one quantifier is within the scope of another quantifier. For example, if this is a quantifier, within the scope, if I put another quantifier, within the scope, if I put another quantifier, okay, then you can see that it will be nesting. So this is basically nested quantifier. This is the situation which is a nested quantifier. Nested quantifier very simple, that in scope of this is the scope of universal quantifier. In this scope, another quantifier is there. So this is your nested quantifier. Now you can have four type of nesting. Like you can have this type of nesting for all x, for all y, alpha. For all x, for all y, alpha. So let's understand this one. When this is true, this is your nesting. When this is true if basically this is saying that, remember this is saying that for every value of x, for every value of y, alpha must be true. Okay. As I told you that domain of x comma y, that can be different, but by default it is same. If no information is given to you, then you have to take the same domain. But if they give you that domain of x is different, domain of y is different, if they give you, then you have to consider domain to be different. But by default you have to consider domain is same. Now we are saying that, let's assume this is the domain of x, ABC. So this is also the domain of y, ABC. Now we are saying that for every x, for every value of x, you take every value of y and that alpha must be true. So it means for every value of x, you take every value of y, this alpha must be true. This alpha must be true. So you can see that whatever combination you take, I can say this alpha x comma y, this must be true. So you can consider this as alpha x comma y. So this is what I'm saying. Now similarly, remember, for every value of x, this would happen. For every value of x, with this you take every value of y. With this you take every value of y. So this should be true. I hope this point is clear. So remember, this is true if and only if for every pair, x comma y, for every pair, what should happen? This alpha must be true. This alpha must be true for every pair. You can take any pair, whatever pair you take, this must be true. Now let's consider another. The next is there exists x, there exists y. Alpha x comma y. What this means? This means that there is some x. Let's assume this is the value ABC and this is ABC. Now we are saying there is some x. There is some x. For example, this x. With this, there is some y. With this, there is some y. That can be this also, that can be this also, that can, but with this x, there is some y such that this alpha CB must be true. Okay. So remember, this is true. This is true if and only if for some pair, please understand, for some pair, for at least one pair x comma y, this alpha is true. Okay. So this is your existential quantifier when the existential quantifier are nested. Now let's see the next. The next is there exists x for all y. What it means? Pxy. This means that there is some value of x. For every value of y, there is some value of x. Like for example, maybe for example this. There is some value of x such that there is some value of x such that for every value of y, with this you take every value of y. With this you take every value of y. What should happen? This p by must be true. This must be true. So I can say this is true if and only if, this is true if and only if there is some fixed x equal to c, or I can say x equal to b. There is some fixed x equal to b. Please understand, there is some fixed x equal to b such that this p b comma y for all y, it is true. Okay. So very simple. There is some fixed value. Such that with this you take everything. There is you can see there is some fixed value. With this you can take everything, and this pxy must be true. Now the last one is for all x there exists y pxy. What this says? It says that for every value of x, for everyone there is someone. Remember, for everyone there is someone. For everyone. Like for every x, there should be someone. Like for this also, there should be someone. For example, for this also, there should be someone. So for everyone there is someone. I can say for every, please understand, this says that for every x, for everyone there is someone. There is some y. For every x there is some y such that this pxy is true. So it simply means for everyone there is someone. Remember, this is important. For everyone there should be someone. It can happen. It is fine. For everyone there is someone. This is also fine. Okay, this is also perfect, no problem. This is also perfect, no problem. Like for everyone there is someone. This is also perfect. The point is for everyone there should be someone. This is also fine, I don't mind. But it should not happen that there are some people for which there is no one. So everything is fine. Like for everyone there is someone. This is also fine. For A there is B, for B there is A, or maybe for B there is C, and for C there is A. So this is also fine. All these things are fine. The point is very simple, that here for everyone there is someone. And here there is someone who is for everyone. There is someone who is for everyone. Please understand. Simple points. So this is the difference between these two. There is someone who is for everyone. And for everyone there is someone. Here someone is for there is someone for everyone. Like this fixed. This someone is fixed. It is fixed for everyone. Okay, and this is saying that for everyone there is someone. For everyone we have someone. Now nothing is fixed. For everyone they can have individual different people. So here it is a fixed who is for everyone. For example, if you want, for example, you can say God. Like God is for everyone. This fixed person, this is for everyone. Okay. And similarly, in this example, you can see analogy like I can say for every person there is a lover. Okay. So you can notice different people, they can have different lover. It is also possible that 2-3 people have the same lover. Okay, so basically all these situations are possible. So remember, all these situations are possible. Like, okay, so this is also possible, or maybe everyone is loving himself or herself. So like that. So all these situations are fine. So remember, this means for everyone there is someone. You know, there is a song in that movie. There is a Bollywood movie. So I there is a song that uh, you know कहते हैं खुदा ने इस जहां में सभी के लिए किसी न किसी को है बनाया. So this is the same situation. सभी के लिए कोई ना कोई. You know, for everyone there is someone, and this means like God is for everyone. So there is a fixed person who is for everyone. This is a fixed person who is for everyone. So like this you can understand. Now let's see this question. Tell me the answer for this one. Tell me the answer for this one. Let me know. What is the answer? So you can see in this question, U is the set of real numbers. Set of real number, this is the domain, this is the universe. Predicate is given to you, that is xy equal to 0. This is the predicate. This predicate is given to you. Pxy means xy is 0. What is the truth value of these statements? See, this statement is saying that for every x, for every y, xy must be 0. It is saying that for every x comma y, for every x comma y, xy must be 0. Of course this is false. Of course this is false, right? This is definitely false, because you are saying that for every x comma y, this xy is 0. Definitely this statement is false, because for example, if you take this pair like 2 comma minus 5, if you take this pair, then definitely for this pair this will be false. Similarly, what about this example? For everyone there is someone. Like for every x there is a y. Okay, we are saying that for every x there is a y, there is someone such that xy is 0. For everyone there is someone such that it is 0. Yes, it is fine, because for everyone there is 0. For everyone there is 0. I can say this is true, this is true. Why this is true? Because for everyone there is 0. You can easily see for every x there is 0. You can take y equal to 0. There is y equal to 0. So you can just take y equal to 0. So this is true. What about this? There is a fixed who is for everyone. There is a fixed, I can say there is someone who is for everyone. Yes, this x you can take as 0. This 0 is for everyone, right? Correct? This x is 0, x equal to 0 for every y. For everyone there is someone. So this is also true. This is saying for someone there is someone. This is also true, because for someone there is someone. Like I can say for this pair you can clearly see this is a true. So this is, you can see like this. What about the answer? What is the answer for this question? For this question, what is the answer? Tell me. On your screen, this is the question. Let me know the answer. Now the predicate is changed. Now we are changing the predicate. The predicate is x divided by y is equal to 1. This is the predicate. You have real numbers, set of real numbers. This is the domain. Now we are saying that this statement is saying that for every x, for every y, x divided by y is 1. So this is definitely false. Why this is false? For example, you can take x equal to 5. You can take y equal to 2. Definitely you can notice that 5 divided by 2 is not equal to 1. Correct? So you can clearly see that this statement is false. What about this statement? For everyone there is someone. For everyone there is someone. For everyone there is someone. Yes. See, for everyone there is someone. I can say for every x, for 1 there is 1. For 2 there is 2. For 3 there is 3. For minus 3 there is 3, minus 3. And so on. So for everyone there is someone. But there is a problem. You can see for everyone there is someone, right? Everything is fine. For example, for 0.5 there is 0.5. Okay, for pi there is pi. For everyone there is someone. But there is a problem. Who is there for 0? For everyone there is someone who is there for 0. So this statement is false, because there is no one for 0. Okay, if you take x equal to 0, then basically there is no one for 0. Is this clear to everyone? So this statement is false because there is no one for 0. This is the problem. There is no one for 0. For 0 there is no 1. What about this? There is a fixed person who is for everyone. So this is also definitely false, because if you take any fixed value, can you put whatever value you want and you will get 1? Definitely not. Okay, so there is no such element, there is no such real number, there is no such real number such that if you divide this by anything, you will always get 1. You will always get 1. So there is nothing such. So you can see this is also false. What about this? This is true. For example, you can consider this pair, this x comma y, you can consider this pair like 5 comma 5 you can take. So definitely this pair you can take. So this is true. I hope this question is clear. Now let me change the question little bit. I am changing this to set of integers. Let's assume set of natural numbers. Set of natural number. When I say set of natural number, then what it means? When I say set of natural number, what it means? It means 1, 2, 3 and so on. So set of natural number like 1, 2, 3 and so on. This is your set of natural number. Now let's assume your question is x is greater than y. So now you tell me the answer for this. X is greater than y. What is the answer now? X greater than y. So can I say whatever 2 you take, x will be greater than y? This is also false, because for example you can take x equal to y, x comma y. This pair you can take, like you can take this pair. This pair you can take. You can clearly see that, or for example you can take this pair. You can clearly see this. For this pair, this value is false. So I can say this is definitely false. What about this? For everyone there is someone. Can I say for every x there is something which is less than this? For example, for 2 there is something less than this. For 2 there is 1. Okay, for 3 there is 2. So can I say for every x there is some y? So I can say, can I say for every x there is some y? Can I say that? Tell me, can I say for every x there is some y? For example, for 10 you have 7. For 10 you have 7. Like for example, for 100 you have 1. So for everyone there is someone. Like I can say whatever you take. For example, for 200 there is 1. So for everyone there is someone. Now you tell me who is there for 1? Who is there for 1? Who is there for 1? So this is false, because there is no one for 1, right? Please understand, there is no one for 1. So this is false. What about this? There is someone who is for everyone. There is someone who is for everyone. This is false, because the reason is very simple, because there is some x which is greater than every y. It says that some x is greater than every y. It says some x is greater than every y. Is there any natural number which is greater than every natural number? Is there, tell me, is there any natural number which is greater than every natural number? Do we have any natural number? Is there any natural number which is greater than every natural number? The answer is no. There is no natural number. There is no natural number which is greater than every natural number. So this is definitely false. Can I say infinity? Can I take x equal to infinity? Please tell me. Can I say infinity is greater than every natural number? Can I take x equal to infinity? Please let me know. Can I take x equal to infinity? Can I do that? I cannot do that, because infinity is not a natural number. Please remember, please understand that infinity is not a integer. Infinity is not a real number. Okay, infinity is not a complex number. Infinity is not a real number. Infinity is an idea. Okay, infinity is not a number. So for example, infinity is not a natural number. So x cannot be infinite. You cannot take x to be infinite, because remember, the domain of x is a natural number and infinity is not a natural number. So you cannot take x equal to infinite, because that is not a natural number. Okay, let's move on. Now let's see this one. There exists x, there exists y, pxy. This is definitely true, because you can take x equal x comma y. This pair you can take as 3 comma 1. Okay, so for this pair definitely it will be true. So this is true. I hope all these points are clear. Can I give this question as a homework? Can I give this question as a homework, like x is less than y? Can I give this question as a homework? So please take this question as a homework. You can write your answer in the comments. Okay, so please write your answers. Okay, in the comments you can write your answer in the comments. So I am giving this question as homework. Another question I am giving you as a homework, that is x is less than equal to y. Okay, so these two questions you can take as homework. You can write your answers. All your answers you can write in the comments. Now let's move on. Let's see this question. Tell me the answer. Quickly tell me the answer for this question. The domain is set of all integers. What is the truth value of these statements? The domain is set of all integer. So what is the truth value of a? This a is saying that for every n, n plus 1 is greater than n. Can I say this? Can I say that for every integer, remember domain is set of integers. So can I say for every integer, this will always happen for every integer? Yes, of course, this will always happen. So this will be true. This will always happen, right? Whatever integer you take, I take any integer, whatever integer you take, then definitely this I plus 1 will be greater than this, right? Correct? This will definitely be greater than. Okay, so this is true. What about this one? This second one. What about the second? There is some n. There is some n. There is some n such that 2n is equal to 3n. There is some n. Yes, this is true. Because you can take n equal to 0. Who is the witness? Who is the witness? Who will make it true? N equal to 0 is the witness. What about the C? What about the next one? Tell me the next one. There is some n such that n is equal to minus n. Again, this is true. Who is the witness? Yes, who is the witness? Tell me, who is the witness? Again, witness is 0. 0 is the witness. This is saying that for everything, for every n, 3n is less than 4n. Can I say? Can I say for every integer, 3n is less than 4n? If you take any integer, can I say this 3n will be less than equal to 4n? So for example, if you take negative also, then what will happen? Like if I take n equal to minus 2, then minus 3, this 3n, this will be basically minus 6. Okay, it will be minus 6. And this will be, this 4n, this will be minus 8. You can see that this is greater. So this statement is basically false, right? If you take n equal to minus 2, then this is a counter example. I can say this is your counter example. This can work as counter example. So this statement is false. So this D is false. Is this understood to everyone? Okay, so like this. Now, anyway, let's move on. Let's see how to convert these statements. We have to convert into English. I'm not going to do all of them, but you just quickly tell me. I'm just telling you what will be the English of this. In English, how will you write this? There exists x nx. Nx means x has visited North Dakota. Nx, that means, and okay, so the domain is set of students. The domain is set of students in your school. Now let's see this. The first is someone has visited North Dakota, correct? Agree or not? This means some student has visited North Dakota, because remember the domain is already given to you. The domain is students. This is the domain, students. So you can see someone has visited North Dakota. Very simple. So here I can say someone has visited North Dakota. What is the second? The second is for all x nx. What it means? Everyone in your school, every student has visited North Dakota. Okay, every student visited North Dakota. What is the C? Negation of there exists nx. See what this is telling you. This is telling you someone visited. What is the negation of someone visited? What is the negation of someone visited? Some student has visited, some student has gone to North Dakota. What is the negation of that? This is saying someone visited. What will be negation of that? Negation of that will be no one visited. Yes or no? Negation will be no one visited North Dakota. Okay. No one visited North Dakota. This will be the negation. Very simple. This is your option C. What about the next option D? Option D is, before option D, you tell me what is option F. Look at option F. Look at option F. That is, for all x, we are saying that, see, for everyone, we are saying that it did not visit North Dakota. For everyone, I am saying it did not visit North Dakota. For everyone, I am saying, for every student, I am saying you did not visit North Dakota. For everyone, you did not visit, you did not visit, you did not visit. So for every student, I am saying that they did not visit North Dakota. It simply means that no one visited North Dakota. Again, I can say. So did you notice that these are basically same? This is an important note you can take. This is an important note you can take, that there exist x and x. If you do the negation of this, then that is same as, remember, if you do negation of existential quantifier, this is the existential quantifier. If you do negation of existential quantifier, you will get universal quantifier negation of x. So means this negation will go inside. This negation, it will go inside. This negation will go inside. This existential quantifier will become universal quantifier. So these are basically same. What about the next? Consider this statement. What this statement is telling you? There is someone who did not visit North Dakota. So there is some student who did not visit North Dakota. Who did not visit North Dakota. Okay, there is some student who did not visit North Dakota. Now you tell me about this one. What this is telling you? What this is telling you? This is telling you negation of everyone visited North Dakota. What is the negation of everyone visited North Dakota? See what this statement is saying. This statement. This is saying that everyone visited. And this is saying negation of that. What is negation of everyone visited? What is that? Negation of everyone visited. Like, let's assume the school principal is saying, this is what school principal is saying, that everyone visited North Dakota. When can I say he is a liar? A school principal is saying that everyone visited North Dakota. When can I say it? He will be liar. Or I can say, when can I say, what is the negation of that? Negation of that will be, someone did not visit. There is some person, there is some student there is some student who did not visit North Dakota. Who did not visit North Dakota. And this is same as, remember, this is same as there is some student who did not visit North Dakota. So this is the another idea, that they are basically same. So these are basically same. So this is also another important point, that what is the negation of universal quantifier? See, you can see this here. The negation of universal quantifier. This is a negation on the universal quantifier. It will be existential quantifier. This negation will go inside. This negation, it is going inside. So it will be same as existential quantifier. The negation is going inside. Okay, so this is the point. Now let's move on. So this is your negation of quantification. Please understand, very simple point, that if you do negation of universal quantifier, you can have anything here, alpha, then that is same as this negation will go inside. Okay, you can keep this negation inside. Then this universal quantifier will become existential quantifier, and this negation will go inside. Similarly, negation of existential quantifier alpha, that will be same as this existential quantifier will become universal, and this negation will go inside. Okay, like this you can do. Now, for example, you can also do this. You can do multiple nested quantifier. You can do, if I have this type of situation, then what I can do, this negation I can send inside. I can send this inside here. So if I send this negation inside here, then this universal quantifier will become existential. It will become existential. The negation will come here, and everything will be same. Okay, so the negation has gone inside. Now I can send this negation inside here also. If I send this negation inside, then this will become universal quantifier. Okay, so it will become like this. This will become universal quantifier, and this negation will go inside. So this negation is propagating from outside to inside. This negation is going inside. So like this also you can do. For example, you can take this as a exercise. You can take that these are basically same. Okay, this you can check that what I'm saying, the negation of this statement, the negation of this. So basically, if I want to find this is same as all of them. All of them are correct. Please understand the negation of this statement. The negation of this statement, that will be this is also correct, this is also correct, this is also correct, this is also correct. All are correct. Because this negation you can send here also. If you send it here, this universal will become existential. Everything else will remain same. So like this you can do. Similarly, the negation of this will be this also, this also, this also, this also. So all are correct. You can check it out. You can apply the De Morgan formula and you can do it, because you know the De Morgan formula. These things are very important, like alpha implies beta. That is same as alpha dash or beta. Another thing is alpha or beta negation will be alpha negation and beta negation. Another is alpha and beta negation. That will be alpha negation or beta negation. Now the next topic is scope of quantifier and bounded and free variable. What is this concept? So scope of quantifier we have already seen. The scope is very simple concept, that scope means where this quantifier will be applicable. So if I give you this quantifier, on which area it will affect, which area will be affected by this quantifier. So for example, in this area, this is the scope of this quantifier. This is the scope. It means, what it means? It means that if you have x here, that will be affected. If you have x here, if you have x here, all these x are same. Please understand. Okay. In this scope, all these x are same, and they are basically, they are bounded by this quantifier. Okay. So these x, this x, this x, this x, they are basically same. They will always be same, and they are bounded by, bounded or quantified. You can say bounded by or quantified by this universal quantifier. Okay, they are bounded by this quantifier. Okay, so this is the point. They are bounded by this quantifier. This is the scope of, but remember, as I told you, like if I give you 4 all x, and let's assume something you have, like px implies qx, let's assume. Okay, and let's assume you have 4 all x, and here you have something called rx XOR px. Now here you can notice, please understand, this is very important, that here you can see that for this quantifier only this is the scope. This quantifier only this is the scope, and for this quantifier only this is the scope. So what it means? It means that this x has nothing to do with this x. This x and this x, they have nothing to do with each other. They are completely independent. These two x, they are completely independent. They have nothing to do with each other. It's like in this area, this is the x, and in this area, this is the x. In this area, this is I can say, this is the dawn in this area, this is the dawn in this area. They can have same name. In different area, same name they can have, of course. Okay. For example, in this area, you have some person Avinash. In this area also, you have some person Avinash. But they are different Avinash. They are not same Avinash. They are different Avinash. Okay. So like that. So I hope this point is clear. So this is the concept of scope. Now, how to handle this? Like if you have this, okay, so what I'm saying, yeah, if you have this, then how to handle this? How to solve this? You can clearly see, you can treat this as alpha, you can treat this as beta. So this is how you can solve. So it is basically nothing but alpha and beta. So they are completely independent of each other. Please understand, this alpha and this beta, they are completely independent. They are completely independent. Okay, so you can solve this alpha separately, you can solve this beta separately, and then you can find the answer. So this is the point of scope. Now, one more thing, for example, if I take this here, if I take this, now you can see that this x is quantified. See, this x look at this x, look at this x, they are quantified, they are bounded by this x. Okay, because this is the scope. So you can easily see that this x is bounded, this x is bounded, this x is bounded. Bounded means quantified. You can call it quantified or you can call it bounded. So bounded means quantified. So these are bounded, and these are bounded by this quantifier, by this, okay, by this quantifier. Now similarly you can see this is also in the scope. So this x is also bounded by, but this is bounded by a different, so this is also bounded. Bounded means quantified. So this x is also bounded by this quantifier. But remember, this x is free, this is completely free, right? Yes or no? This x is free, this is not bounded by anyone, because this is the scope of this quantifier. So you can see this x is completely free variable. This is called free variable because it is not quantified by any quantifier. Bounded means quantified. This x is quantified, this is quantified by this quantifier, this x is quantified by this quantifier. These two x are same, these two x are same. This x has nothing to do with this x. Okay, this x has nothing to do with this x. Also this x has nothing to do with this x. You can see this is a free x because it is not quantified by any quantifier. So this is the point. Similarly you can see that, like for example, this is the area where x is living. The variable x lives here because this is the scope. As you can see, this is the scope of this quantifier, for this quantifier. So this is what I'm saying, that you can see for this quantifier, look at this quantifier. For this quantifier, this is the scope. And for this quantifier, this is the scope. This is known as scope. This is known as scope. So you can see that this variable x lives here and this variable y lives here. Similarly, remember, now you can notice this variable x lives here, this variable x lives here, but they are different variable. Please understand. This variable x lives here, a different variable with the same name, a different variable lives here. So you can notice this x has nothing to do with this x. They are completely independent. So this is a different area, this is a different area, and you can treat like this is alpha, this is beta. So finally this is your alpha and beta. So this is the idea of free and bounded variable. So what is a free variable? What is a bounded variable? If you apply a quantifier on a variable, that will be called bounded variable. If you don't apply any quantifier on a variable, that is called free variable. Like you can notice in this, there exists x for all y. Here you can notice this is also bounded, this x is also bounded, and this y is also bounded. So both are basically bounded, both x, y are bounded. Now you can check it out that this x is definitely bounded, but this y is free. This y is not quantified. There is no quantifier on this y. So this y is free. So a variable is free. When can you say a variable is free? If it is not referred by any quantifier. A variable is bounded. When can you say a variable is bounded? If it is referred by a quantifier. So bounded variable means quantified variable, and free variable means a non-quantified variable. Now the important point that you have to understand. Okay. So let's see something important. Now you tell me a simple question I am asking you. Look at this px. X is prime. Let's assume domain of x is set of natural number. I am giving you domain of x, that is set of natural number. You tell me this x, is this free or bounded? Look at this x. Is this x free or bounded? Tell me. This x, is this free or is this x bounded? Let me know. So this is clearly this is free. You can replace this with any value. This is definitely free. So this variable, you can notice this is definitely free. It is free. So because it is free, so you can, of course, you can replace this x, you can replace with any value in the domain. So can I say true or false? Can I say this px? Can you tell me the truth value of px? Can you tell me the truth value of px? Can you tell me that? What is the truth value of px? Let me know. This x is free. This x is completely free. You can replace this. This is a free variable. So this you can replace with any value from the domain. What is the truth value of P? The answer is this is not a this is not a proposition, right? There is no truth value. Why there is no truth value? Why? There is no truth value. Why there is no truth value? What is the reason there is no truth value? The reason there is no truth value is because here X is free. Okay, because this is not a proposition. Why this is not a proposition? Because X is free. So this is not a proposition. Please understand. This is not a proposition since X is free. So this X is a free variable. So that is the reason this is not a proposition. This Px, this is not a proposition. X is prime. So the value will depend on, you can clearly see this truth value will depend on what? It will depend on X. It will depend on X. So this is not a proposition. This Px. So when you have free variable, then your statement is not a proposition. So this is the note. Okay. So I can say sentence containing free variable. Containing free variable. If you have free variable, so sentence containing free variable is not a proposition. Is not a proposition. So if you have free variable, then definitely that is not a proposition. So sentence which contains free variable, that is not a proposition. Okay. The second point you can see in the same question, if I ask you what is P2 or maybe for example what is P5, then you can say that is true. Then it is a proposition. So because now there is no free variable, right? Yes or no? In this P5, what this P5 is? This P5 is prime. Now there is no free variable, right? Now in this there is no free variable. Because there is no free variable, so that is the reason this is the reason this is proposition. It is proposition because there is no free variable. We don't have any free variable, so this is a proposition. Okay. The second thing I can ask you, the same question. In the same question, if I ask you for all x px, what is that? Is that a proposition? Is that a proposition? I am saying for all x px. Is that a proposition? Yes, now this is a proposition because now there is no free variable x. In this you can notice now there is no free x. Now you don't have any free x. Now this x is bounded. This x is now bounded variable. So now you can say this is a proposition, which is false because everyone is not a prime number. So this is false. But you can notice there is no free x now. Now this is a bounded variable. Okay, so this is the simple point. Similarly, you can notice if I apply this, there exists x. Now this is also proposition. This is also proposition. Of course, this is a true proposition. This will be true. Again, you can notice this is a bounded variable. So these are bounded variables. This is the difference of bounded variable and free variable. You tell me a simple question. A simple question you tell me. If I say that there is no free variable, let's assume there is, this is the question. Let's assume there is some alpha you have. Alpha does not contain free variable. Let's assume alpha does not contain free variable x. Alpha does not contain free variable x. In this alpha, you don't have any free variable x in this alpha. Okay, so alpha does not contain free variable x. It does not contain. Then what is for all x alpha? And what is there exist x alpha? Can anyone tell me? What is the answer? Tell me. Alpha does not contain free variable x. In this alpha, there is alpha. In this alpha, there is no free x. In this alpha, you have no free x. There is no free x. So if there is no free x, I can say, if there is no free x, can I say alpha does not depend on x? Can I say alpha is independent of x? Can I say? Tell me, can I say alpha is independent of x? Can I say this? Because in this alpha, you have no free x. There is no free variable x. So can I say this alpha is completely, like I can say independent of x. This alpha, this is independent of x. There is no free x. So because there is no free x, in this alpha, there is no free variable x. So it means this alpha is not dependent on x. It is independent of x. So that is the reason this is same as alpha and this is also same as alpha. Yes or no? Both are same as alpha. Both are equivalent to alpha. Is this clear to everyone? This is a very important point because sometimes they will give you this. This is what they will say. They will say that A does not contain free x. A does not contain free x. This is what they will say. They will say A does not contain free x. This statement, what it means, let me tell you what this statement means. This statement simply means that this statement simply means that A does not depend on x. A does not depend on x. Okay, A does not depend on x. So this A is unaffected by this. So okay, and this means what? This means that if I do for all x A, that will be same as A. Okay, if I do this, that will be equivalent to A. So the quantifier on x cannot affect it. The quantifier on x cannot affect A. Okay, so this will have the same truth value as A. This will have the same truth value as A. Now you might be thinking, like if I give you this question, for all x is greater than 4, and let me assume domain is set of natural number. Now you tell me, in this do we have free x? In this do we have free x? Tell me. Is there any free x? There is no free x, right? In this there is no free x. I am saying that no free x means it does not depend on x. Can I say it depends on x? Does it depend on x? A simple question I am asking. Does it depend on x? Simple question I am asking. Does it depend on x? Does it depend on x? Does it depend on x? The answer is no. This is a proposition, so it cannot depend on the variable. Do you agree or not? The answer is no. Why? Because this is a proposition. A proposition does not depend on any variable. Do you agree? A proposition is always true or false. Proposition never depends on, this is a proposition, and remember, proposition never depends on any variable. Is this clear? Never depends on any variable. Okay, is this clear to everyone? Please, this is a common sense. See, this is simple common sense that this is a proposition. X is greater than 4. This is a proposition. You can clearly see this is false. Domain is set of natural number. You can clearly see this is false. Because this is false, so it does not depend on any variable, of course. A proposition never depends on any variable. So this also does not depend on x. Remember, this is the point I want to tell you. I want to tell you that A does not have free variable x. It simply means that it does not depend on x. So remember, this does not depend on x. Please understand. This does not depend on x. Why? Because this x you can change. This is same as y. You can make it y, no problem. You can make it z, no problem. Okay, because these are bounded variable. Okay, these are quantified variable. Please understand. These are quantified. These are not free. These are quantified. These are not free. Okay, so you can just change their name, no problem. You can change the name. You can change the name. There is no problem. So this is what I want to tell you, that if you have no free variable x, A does not contain any free variable x, it simply means that A does not depend on x. A will not depend on x. If A does not depend on x, then universal quantifier, any quantifier on x will not affect it. Is this understood? Let me know. This is the summary. Clear? So this is the summary of bounded variable, free variable. Of course, the details, if you want, the details you can find in the goclasses discrete mathematics course. There you can find all the details. But this is the summary, all the important points I told you. These are the points you have to understand. These are the points you have to remember. Okay. So very simple. These are the points. These important points you have to remember. Now let's move on. So let's see this. In this, how many free variables are there? In this question, how many free variables are there? Please understand that this and this and this, these are the for this open parenthesis, this is the closed parenthesis. For this open parenthesis, this is the closed parenthesis. So I can say this is the scope, right? Correct? Can I say this is the scope? This entire scope y. Okay, this is the entire scope of y. This is the entire scope of this for all y. Entire scope of for all y. This is the entire scope, because you can notice this is a open parenthesis. For this open parenthesis, this is the closed parenthesis. This is the closed parenthesis. Okay, so now the question is asking which of how many free variables do we have? You can notice this is bounded. Definitely this is bounded, because you can see it is in the scope of for all y. This is in the scope of for all y, so this y is bounded. Yeah, this is free, right? This x is free. This x is free. Now you can see what is the scope of this universe, this quantifier. Look at this. For this quantifier, for this for all x, what is the scope? For this is the scope. Because this is the scope, so definitely this is bounded. Correct? Definitely this is bounded. This is bounded. Remember, this is also bounded because it is bounded by for all. It is bounded by the outside for all. Okay, remember, this is bounded by this outside for all. This is bounded by outside for all quantifier. This z is free. Yes, this z is free. This z is free. So finally, answer will be 2. There are 2 free variables in this question. Okay, we have total 2 free variables. I hope this point is clear. Is this clear to everyone? Now let's see this question. Whatever we have seen, let's summarize that with this question. If you can answer this question, you understood bounded variable, free variable. Let's see this. How to create a proposition or a statement. How to create a proposition from a predicate. If I give you a predicate, how to create a proposition. You want to create a proposition from a predicate, then how to do that? Tell me the answer for this question. Please tell me. Think about it. Okay, so let's see. Let's see the answer. How to create a proposition from a predicate. Every variable must be either bounded, either it should be bounded, or it should be replaced by some value from the domain. Yes, this is correct. Either you replace with some value from the domain or you keep it bounded. For example, consider this question like, if I give you some expression pxy, I am giving you this expression pxy, and this pxy is, let's assume x is greater than y. Okay, x is greater than y. Now, let me assume that domain is or maybe I can say x is greater than equal to y. X is greater than equal to y. Let's assume the domain is set of natural number. This is the domain 1, 2, 3 and so on. Now, you can clearly see this is not a proposition. This is not a proposition. Why this is not a proposition? Because these are free variables. The reason is simple, that these are the free variables. These are free variables. So because these are the free variables, so this is not a proposition. Now what you can do? There are many ways to create a proposition. Now let's create propositions. You have many ways to create a proposition. How can you create proposition? The first way that you have is, what you can do, you can make everything bounded. Let's make everything bounded. Okay, let me make everything bounded. Now you can notice every variable is bounded. Okay, so now you can notice x comma y, these are bounded. X is also bounded, y is also bounded. So tell me, what is the truth value of this? Now this is a proposition. Because everything is a bounded, nothing is free. Now this is a proposition. Tell me, what is the truth value of this? For every x there is a y. For every x there is a y. Yes, this is true. correct? For everyone there is someone, like you can see that for everyone there is someone. For 1 there is 1, for 2 there is 1, for 3 there is 1, for 4 there is 2, for everyone there is someone. So you can see this is true. Okay, so this is how you can create proposition. What is another way to create proposition? Tell me, what is the another way to create proposition? You can replace every variable with a specific value. You can replace this with 10, you can replace this with 5, or you can replace this with 15. This is what you can do. So you can notice 10 is greater than equal to 15. Again, this is a proposition. Please understand, again this is a proposition. So again this is a, you can see this is again this is false. So again this is a proposition. Another way, what is the another way to create a proposition? The another way to create a proposition is you can bound, for example, I can bound this x. For example, I can bound this x, and I can put a specific value for y. I can bound this x and this y. For this y, I can put a specific value. I can put a specific value for this y. So of course this is false, but this is a proposition. But this is a proposition. But this is a proposition. So did you understand what is happening here? How to create a proposition? Either you can create everything bounded, either every variable you make bounded, or you replace every variable by a specific value. Okay, every variable you replace by a specific value, or you can make this some variables bounded, the remaining variables you can replace by a specific value. Very simple. So like this you can create proposition. So every variable must either be bounded or it must be replaced with some value from the domain. Every variable must be either free. This is not correct. B is not correct. There should be no free variable. Yes, this is correct. There should be no free variable. There should be no bounded variable. This is not correct. So the answer will be A, C. Answer is going to be A, C. Clear? Is this clear to everyone? Is this understood to everyone? Very simple. Okay, so this is how you can do. Now let's see this question. What is the answer for this one? See, one note I want to tell you. If I statement like this, let's assume this is the domain. The domain is set of natural number. Let me assume, and I want to say that for every x which is greater than 4, for every x which is greater than 4, this is what I want to say. I want to say for every x which is greater than 4, every prime is odd. For every x greater than 4, primes, if x is prime, x is odd. If x is prime, x is odd. Then how to write this? This is what I want to write. Please understand. This is what I want to write. I want to write that for every x greater than 4, if x is prime, x is odd. If x is prime, then definitely x is odd. So how to write this? How can I write this? So you can easily see this is, if you want to write this, you can easily do this. Either you can do this, that for every x, for all x, you put it here, that for all x greater than 4, you put it here. What you are saying? You are saying that for all x greater than 4, you put it here. And then you simply say that if it is prime, then it is odd. So this is correct. Remember, this is correct. So you can put it here. You can put it here. Or what you can do, you can do this for all x, or you can do this for all x. If it is greater than 4 and it is prime, if it is greater than 4 and it is prime, okay, if it is greater than 4 and it is prime, then it is odd. This is also correct. So these are correct. Is this clear? So both are correct. Either you can put it here, or you can do like this. For every x, if it is greater than 4 and it is prime, if this happens, then this will be odd. Like this you can write. So what is the important point that I want to tell you is this. If you have this type of situation that for all x, let's assume the original domain is this. Let's assume original domain is, for example, D. This is the domain. But you want to say that this is your domain. In this domain, let's assume there is some part which is let's assume that is M. In this domain, there is a subset which is M. Now, if you want to say that for all x belonging to M, this Px happens. Okay, this px happens. Then how can I write it? Another way of writing this, you are saying that, what you are saying? You are saying for all x in this, for all x in this, for every x in this must be true. For everyone here, this p must be true. So I can say that for every x, this is how I can write. For every x, if it is in M, okay, if it is in M, if it belongs to M, then px. Or you can also say that for all x, I can also say for all x, if mx, then px. So this is how you can write all these things. So remember, for everyone here, p is true. Means if you are here, then p is true. If you are in M, then p is true. If you are mx, then px is true. So this is how you can do. The another is existential quantifier. We are saying that there is some x here, there is someone here, such that this px is true. So what I can say? I can say that there is someone who is here also, and for which px is also true. You can also write like this, that there is someone for which is mx is also true and px is also true. So this is how you can do. I hope these points are clear. Let me know, are these understood? Okay, so can you solve this question? What is the answer for this question? Can you tell me? The domain is already given to you, set of real numbers. Now you are saying that for all x less than 0, x square is greater than 0. For all x less than 0, for every x which is less than 0, x square is greater than 0. Yes, this is true, right? Of course, this is true. This is definitely true. You can also write like this. For all x less than 0, x square is greater than 0. This same statement you can also write like this, that for all x, if it is less than 0, then x square is greater than 0. Okay, so this is also true. This is also true. So this is how you can do. Very simple question. Now let's see the next. This one. What this is saying? This is saying that for all y which are not 0, for all y which is not 0, y cube is also not 0. This is also true. This is also true. The same statement you can also write that for all y, you can say that if it is not 0, if this y is not 0, then y cube is also not 0. Okay, so this is how you can, of course, this is also true. If y is not 0, then y cube can also not be 0. What about this one? What about this one? This is saying that there exists a z which is greater than 0, such that z square is equal to 2. There is some z greater than 0, such that z square is 0. Yeah, this is also true. Why this is true? What is the reason this is true? Because there is a witness. You can take witness. The witness can be z equal to square root of 2. So this you can take as witness. So like this. So this is also true. Also, I want to tell you that if you want to say that there is a z which is greater than 0, such that z square is 2, the same statement you can write like this, that there is a z such that it is greater than 0 and its square is 2. Okay, so like this you can write all these points. All these points you can write like this. So all are true. Can I give this question as a homework? So please take this question as a homework. We have done enough. So take this question as a homework and you can write your answer in the comments. Okay. So let's in the comments you can write. Comment your answer. So you can take this question. You can solve this question after this video is over. So you can solve after some time, or if you are watching this as a recorded, then you can pause the video, you can solve it, and you can write your answer in the comments. So comment your answer for this question. Okay, that's your summary. Everything we have seen. This is the summary lecture.